burrowing and such shortly after deposition gives us a lot of information. We can learn things about past climates, and then some of the diagenetic structures that are present within the rock will tell us about the burial history. A very interesting course that I took as a graduate student at the University of Colorado from Ted Walker, Red Bed Ted, as many call him. We would take thin sections, and we would have to take those thin sections and use relative dating, cross-cutting relationships, and so forth to determine the burial history of the rock. What alteration came first? What came second? How deeply was the rock buried? From these indicators and so forth. Very interesting course. Okay, so let's start off with classification. What are the categories that we find for sedimentary structures? And again, here there's not entire agreement on how to perform the classification. There are two primary ways in which this is done. One of those is by the process through which the sedimentary structure was formed. And so we'll divide those into physical, chemical, and biological structures. Physical structures are those that are produced by fluid flow, by gravity, compaction, and so forth. The chemical structures will be those that have to do with dissolution and replacement of minerals, and biological are related to organisms. Okay, for our discussion today, I'm going to focus solely on the physical structures. Another manner in which we classify structures is based on timing. So we'll use terms such as primary, secondary, and tertiary. And before the structures are formed, often there will be some erosional features that are associated with them. And so the primary structures are the ones that form at the time that the sediment accumulates. So as the sediment is being deposited, we'll see cross-bedding, ripple marks. We can have stromatolites, that is biological processes that are accumulating sediment. Those are the primary features. The ones that are referred to as secondary are the ones that happen after deposition, but prior to burial. Things such as desiccation cracks, rain imprints, slumping to form contorted bedding, loading features, and so bioturbation is another one of those. And then the diagenetic or tertiary structures are those that are produced once the sediment has been buried. Nodules and concretions are something we often see in outcrop. A lot of the mineral replacement and dissolution we'll see under a microscope, and pressure solution and so forth. So again, here I'm going to focus on the primary sedimentary structures for our discussion today. And so we're talking about the physical structures that were formed at the time of deposition. Okay, one other thing that I want to at least mention before I get into the details is the difference between bed forms and deep. The bed form is the overall three-dimensional feature that houses the sedimentary structures. Sometimes we refer to bed forms as structures, and other times we like to consider those a little bit differently. So the bed form in this case would be a sand dune. The bedding would be the cross bedding that's found within that sand dune, or a ripple mark versus the cross bedding that's present within the ripple. All right. Okay. Now, primary sedimentary structures, physical structures, can be formed in three major ways: from settling from suspension, through traction, and through fluid flow. Suspension is related mostly to the accumulation of mud in very quiet water environments, such as the ocean floor, the bottom of a lake or a lagoon, possibly a floodplain during the waning stages of flooding. This occurs primarily as particles flocculate, that is, they group together, they clump together, and then they fall out as sediment. On the other end of the spectrum, flow, those are features that are formed through gravity. Debris flows, turbidites are the ones that are primarily preserved in the rock record. And I'll talk a little bit about each of those, but again, I'm going to talk mostly today because the things that I work with, these are the most useful structures, or the ones that I see the most, are those that are produced by traction. That is, a fluid is moving over a surface, is picking up particles, and is transporting them along the surface as bed load, or there can be a temporary suspension and return to the bed load. Okay, so part of that, many of you are probably familiar with the Hjulstrom diagram. In 1939, Hjulstrom developed this, and the idea was to determine for a particular depth of water and grain size, what the flow velocity would be to cause those particles to start to move and to stop to move. So to become entrained and then to become deposited. So as you look at this diagram, there's the blue at the top, and there's a surface underneath that that says erosion velocity curve. That represents, for a particular grain size, the flow velocity that is required to begin to move unconsolidated sedimentary particles. Something that is not intuitive about this, when I ask the question in my classes of students, if I have mud, sand, and gravel, which will begin to be transported first, the response is almost always mud. And that's because with rock, shales do tend to erode more quickly than a sandstone, but that has to do more with cementation than with the actual size of the particles. But there's some characteristics about mud, particularly with the clay particles, that tend to stick together and prevent them from being moved very easily. So actually, the first particles that tend to move are those that are in about the medium sand range. And then as the flow velocity increases, then we'll start to move clay, and we'll also start to move the gravel. And so on the other side of the spectrum, the settling velocity, and notice that this is a logarithmic scale on here. What are the particles to be deposited first? Those are the gravel particles. So notice that gravel is only in transport in that gray field for a very small range of velocities. Or the velocity has to be quite high, and then as soon as we drop to that velocity, the sediment drops out again. So the settling is very rapid for large particles and very slow for the smaller particles. Okay, and that will come into play with as we go through the discussion here. Okay, so let's start with deposition from suspension. The primary sedimentary structure that we will see in mudstones is parallel laminations. Now these can be bioturbated later, but that's a secondary feature. The primary structure that we're going to see in mudstone is parallel lamination. On the right, I have a couple of photographs. There's one of the Mississippi Delta, and you can see in this image that the mud from the delta manages to move a significant distance into the basin, where it then settles out to the sea floor. Down at the bottom is a picture from a reservoir here in Idaho, and you can see the plume of mud as it is moving out into the basin. And so, in terms of the very fine-grained sediment, there really are not a lot of sedimentary structures associated, primary sedimentary structures, because of the necessity of very low flow velocities for the mud to accumulate. Now, in the picture on the left, you can see a few bands in there that are a little bit coarser, a little bit more resistant. A few of those are a little bit more silty, and so there can be some high energy events that bring silt out into the basin. And a few of those are actually very thin limestones that are formed during times of sediment starvation, when there's almost no clastic sediment that's being deposited. Okay, most of my discussion is going to deal with this next category, what we refer to as flow regime structures. Now, flow regime refers to a sequence of formation of structures related to an increase in energy, that is in flow velocity. And the idea here is that if we start off with a bed of sediment that has no relief on it, just a flat bed. It consists of sand, in most cases, and water begins, or wind, begins to flow across the surface. That fluid is going to pick up the particles, and it's going to start to put them into piles. Okay, those piles we call ripples. And ripples are fairly small features, but as the flow velocity increases, the ripples tend to become fewer in number, but larger in size. However, they're, looking back at the Hjulstrom diagram, there is a flow velocity at which the particles can no longer accumulate and they begin to erode. So looking at the left, we go from ripples into sand waves, into dunes, and then once we get to the dune stage, if flow velocity increases further, then the dunes begin to flatten out as the rate of erosion starts to catch up with the rate of deposition. And once the rate of deposition and the rate of erosion are pretty much equal, then we switch from lower flow regime into upper flow regime. Now, where I have F equals 1 on there, that refers to the Froude number. And by definition, the boundary between lower flow regime and upper flow regime is a Froude number of 1. Okay. As the sedimentary structures then, or as the flow velocity continues to increase, we get closer and closer to the state of erosion rather than deposition, and we'll see a transition from plain beds into anti-dunes, and then finally into an erosional situation where the sediment is simply being removed. And I'll talk about that in some detail as we go through. The middle diagram is to show that there's actually some complication in here, that depending on the grain size, some of these steps might be skipped, but we won't get into that much detail right now. Okay, so let's start with the small features, the ripples, and moving into dunes. Now, there are different classifications out there. The one that I tend to see the most often is that ripples are restricted to about 0.5 centimeter to 3 centimeters in height, and 5 to 40 centimeters in wavelength. Not everybody agrees with that number, and I don't think that very many of us actually go into the field and make those kind of measurements. We tend to just look at things and be a little more descriptive. I think that there are times when we get a little bit carried away with trying to overly classify things. The concept, I think, is what is significant here, is that ripples are small. As the flow velocity increases, if there is a significant enough sediment supply, those ripples will grow into larger features, which might be called sand waves, and then dunes. But even that terminology is not used uniformly. I remember back in the 80s and the 90s, a lot of people were trying to change it to microforms, mesoforms, and macroforms, and there have been a variety of attempts to do the classification. But I think that most of us know what a ripple is. We've all seen these small features on the bottom of a river or a lake or in a gutter along the street. Okay, so then ripples, we will classify into a number of ways. One of the popular ways to classify ripples is by the plan morphology, that is looking at them from the top. And I'm not going to talk about all of these today. I'll talk about a number of them. But the reason that we see a number of geometries in the ripples has to do with a balance between the flow velocity and the sediment supply. So if we have a lot of sediment, we'll tend to see some of the structures such as in the top row, and we tend to see with a lower sediment supply or a higher flow velocity for that sediment supply, the ripple shapes that are down at the bottom, and we transition through these. Other things that can affect it is the flow in one direction. Is the flow bidirectional? Is the flow circular, such as on a beach? There are a number of things that can affect the plan geometry of ripples. Now, most of us tend to refer to ripples as either straight crested, sinuous crested, or isolated. Sometimes we'll call them two-dimensional or three-dimensional. And down at the bottom on the right, you can see again the transition as you move from left to right. You're seeing either an increase in flow velocity for a given amount of sediment, or you're looking at a decrease in sediment supply for a fixed flow velocity. Grain size can also have an impact on that. But straight crested ripples, you see on the left, and sinuous, where they're a little bit more curved in the middle. And on this one, I've tried to pick somewhere. In this case, you can see there's a little bit lower sediment supply in that middle one. The one on the right, a lot of sediment but very high flow velocity was required to produce those. Another way that we will classify ripples is on their cross-section morphology. Primarily, are the ripples asymmetrical or are they symmetrical? So on the left are asymmetrical ripples, and it's going through a variety. But as you go down and move to the right, we actually have a significant range of asymmetrical ripples, whereas the symmetrical are a little bit more confined. So asymmetrical means that there is a gentle upcurrent side and a steep downcurrent side to the ripple. The symmetrical ripples, both sides tend to have about the same inclination. It won't be exact. Sometimes we refer to the asymmetrical ripples as current generated ripples. And the thought here is that you're looking primarily at ripples that are formed by a single direction of flow. With the symmetrical ripples, we sometimes refer to those as wave generated, and that has to do with the oscillatory flow. I've got a video here I'll show in a little bit where you can see that there's a pulse of the wave that pushes the ripple one direction, and then it comes back in the opposite direction. There still is an overall transport direction, so the cross-bedding will probably dip mostly in one direction, but the ripples tend to be a little bit more symmetrical. Now, I hesitate to use the words current generated and wave generated as classification terms because those are interpretations. Currents and waves indicate the manner in which they were formed. So I much prefer using the terms asymmetrical and symmetrical, but then interpreting them as having been formed by currents or by waves. Okay, so the internal structure of these features is what we call cross-bedding. Cross-bedding refers to sedimentary structures that have an inclination between the top of the bed and the bottom of the bed. So the top of the bed will be relatively flat, the bottom of the bed will be relatively flat, and the laminations between those two surfaces will be inclined in a particular direction, and that direction can be used to interpret the direction of fluid flow. I'm sure that most of you have seen a diagram such as the one in the middle here, where a ripple or a dune is formed as the wind or water, in this case, move from the left to the right. And as they do so, they will erode sediment off of the gentle slope, and it will avalanche down the front to form the crossbed pattern. And I've got a couple of videos down here to demonstrate this. Some of these are old and poor resolution. But notice that as the grains are moving from left to right, you can see them avalanching down the front, and that's going to form the inclined geometry that you see in the ripples. For some reason, the resolution looks really bad on this right now. Okay, let me speed that up just a little bit. There we go. Okay, here's a little bit closer in, and you can actually see the avalanching down the front of the ripple, and dunes form in the same manner. Okay. Let's see. I'm going to skip that middle one there for time. The picture on the right. Another, and you probably saw this in that video as well, another characteristic of these dunes is there tends to be up here along the crest of the dune what we call flow separation. So the coarser particles are moving up the dune by traction, and they avalanche down the other side. The finer particles can remain airborne or waterborne for some distance, and can even rest on the back of the dune that is that's ahead of them as this migrates up, and that can form another set of sedimentary structures. And here's a little video I made just a couple of weeks ago when I took my grandson up to the top of this dune. This is here in Idaho. The wind was blowing. I'll zoom in here in a moment, but you can see the wind is blowing from left to right, and right there we've got avalanche that's coming down. The avalanche is hard to see in this picture, but then some of the sediment is airborne and is moving further down the dune before it settles. So in essence, we have a bed load and a suspended load associated with this dune formation. Okay, so let's go back to the ripples and dunes. The things I'm talking about here refers to both. The only difference between a ripple and a dune is their size. And so we will often divide the cross bedding within a ripple or dune into trough. These are the three-dimensional ripples, the ones that have the sinuous crest, and into planar cross bedding. Trough cross bedding gets its name from the fact that in a longitudinal view, it flattens from the top down toward the base, and in a transverse view, if you look at the diagram over here, over here on the left, it has these kind of trough, these little smiley shapes associated with it. But the geometry of the dune is what affects the development of the development of troughs. Environments in which these are very common, we'll often find them in the subaqueous part of a point bar, such as the upper right photo, and then beneath the waves over here, before the crashing, a little bit further back, where the waves are causing longshore transport along the coast. And so again, here are a couple of videos that show the formation of trough crossbeds. Okay, now, one of the things I like about these diagrams as they spin around is when we look at an outcrop, we tend to think that we're looking either in the direction that the fluid is flowing, or we're looking perpendicular to it. Whereas in most cases, what we're going to see is an aspect that is at some angle to the fluid flow. And that can create some complications in making paleocurrent measurements. And so I'll just show that one for right now. So planar cross bedding, this is also called tabular. Some call it planar tabular. Some refer to it as wedge. Others call it two-dimensional. So again, there are a lot of different names that you're going to see in the literature for this. Planar cross bedding is produced. Well, first of all, it is cross bedding where there is very little change in dip angle from the top of the bed down to the bottom of the bed. Now notice on this one, rather than a meandering river, the example that I have is a braided stream. I've also got sand dunes down here as well. We do tend to see planar cross-bedding more frequently in braided rivers than in meandering rivers. But the reason for that is because of the very high sediment supply. And as the amount of sediment increases, there tends to be a transition, as I mentioned earlier, from the trough into the planar cross-bedding, or as flow velocity it decreases. Another little video down here for this one. Now notice geometrically, this one does not have, in the direction of transport, it does not have the little trough or smiley shaped features associated with it. So this one, if you were to look at it in a transverse section, it would almost appear as parallel laminations. And so it's important that you understand the importance of aspect. So again, when this gets up to the top, it'll rotate and it'll cut off the top. It'll erode the top of the bed. So notice that depending on how you're looking at the outcrop, there can be quite a different perspective for the cross bedding. Okay. All right. So with the to the asymmetrical aspect of this versus symmetrical, the current versus wave. Asymmetrical ripples, as I've said, are produced by single flow or by fluid flow that is mostly in one direction. Internally, the cross bedding, as we saw in the previous diagram, is going to be mostly unidirectional. And what I've got here on the right, this is a picture. I'm standing on a point bar in a river here in Idaho. The flow is from the left to the right in this photo. This surface that I'm standing on has been bioturbated. There's some ripples on it, but down below the water level where the river continues to flow, there are some small dunes that are migrating. Notice that they are sinuous crested dunes, and they are producing a trough type of cross bedding. This other photograph comes from a beach. And in this case, the flow that is moving in is much stronger than the flow that is moving out and is causing the ripples to be asymmetrical. You get both asymmetrical and symmetrical ripples that are present on a beach. And so here's a picture of asymmetrical ripples that are formed in a flume. Okay, I'm going to cut some of those a little bit short. Okay, so the oscillatory ripples. Okay, notice that these ones look quite a bit different. They're more continuous. They often will bifurcate into more than one ripple. The two slopes are pretty much equal in their slope angle. On this, you see that I've put a beach in here once again because we can find asymmetrical and symmetrical ripples both on the beach. The upper photograph is a tidal flat, which also has a wide variety of ripples. But these are formed by the circular motion of a wave. So as a wave moves over the surface and comes into contact with the surface, it tends to push the sediment forward, and then the energy moves up and it pushes it back, and the wave comes back down. That can be seen quite nicely in a couple of flumes here. Okay, this one, so this is a wave tank. In this case, the energy is coming from right to left, but you can see by the algae in there that these waves are subjected to two directions of current. Here it is from the side. Now, the stronger current, in this case from left to right, before it was from right to left, the stronger current is from left to right. And so that is the direction that the dune is migrating. That's the direction that is going to preserve the cross bedding. However, that backflow from the circular motion of the wave is going to prevent the ripple from having the very steep slip face that you see in the asymmetrical dunes. And if I can. Okay, another wave tank experiment. Now I like this video because you can see the sediment moving in both directions. But the strongest flow is from left to right, and that's what's going to preserve the cross bedding. It's the top of the ripple that's kind of removed as the flow moves back to the left. Yep. Okay, this is starting with a flat bed, and you're watching the ripples develop on that bed. And notice that because of the oscillatory motion, in this case a high amount of sediment, the ripples tend to be straight crested. And internally they will be dominated by planar cross stratification. And anyway, an interesting video. I'll make this available to you if you want to watch the rest of it. Okay, those are the two types of ripples that we focus on most of the time. They're the ones that we see most commonly. But there are other types of ripples, and I want to go ahead and go through a few of these because some of them are quite important. One of them is referred to as a flat top ripple. In the literature, you'll also see them called bidirectional or decapitated ripples. And I prefer the descriptive term flat top because that avoids any type of an interpretation. These are very commonly found on tidal flats. And in this case, what you're seeing is the result of two directions of flow. So as the tides come in, they pick up the sand. The sand will migrate landward and form a ripple. And then as the tide moves back out, it will actually decapitate, means cut off. It will actually remove the top of that ripple and deposit it in the other direction. And I'm not very good at using a whiteboard with a mouse, so I'm going to avoid that here. But if I had a whiteboard, what I would draw is I would draw a ripple with cross bedding that is dipping in the landward direction, and then I would take the eraser and I would remove the top of the ripple, make it flat, and then the backward flow. There could be see, somebody else is drawing on there for me. If I can, let me get the, can you guys see that cursor okay? Hope you can. But see how flat the top of that ripple is and the top of this one is? And so the flow will come in one way, produce the ripple, and then it goes back the other way. It takes the sediment off here, and it will form a second little ripple on the downslope side of the previous. And so sometimes you can actually see two directions of transport, two directions of dip within the ripple marks. And again, the only place that I'm aware of for these to form is in a tidal setting, where the tides come in, create the ripple, the tides go back out, they cut off the top of the ripple and redeposit the sediment. So these are a good indicator of, maybe not a tidal flat, but that tidal currents are present. Another common type of ripple, particularly in tidal areas, the pictures I've got on the right, the bottom is a tidal flat, the one at the top is a lake bottom. These are called interference ripples, and that's because of the pattern that they are produced. I can remember way back when I was in high school, back in the 1970s, there was an experiment that I thought was pretty interesting, where my physics teacher put a bunch of sand onto a metal plate, and he pushed a button and it started to vibrate. And as it vibrated, the sand would form these piles called nodes that were almost equally spaced with little troughs that were in between. That's the kind of pattern that we see here with these interference ripples. And the way they are formed, I'll show you the video here in a moment, is that you have currents that are approaching them from different angles at the same time. And so if you look at the tidal flat picture in the lower right-hand part of the slide, you can see all the little ponds that are sitting there during low tide. As the wind blows across that, the waves will bounce off the margins of the ponds, and the wave energy will interfere with itself from the opposite sides. This little video right here has a couple of pins that are poking down into the surface of the water, and notice that as the waves interfere with one another, they form this pattern of nodes and troughs. And these tend to form in very shallow water. And again, most of the time, most of the places where I've seen them have been in tidal deposits, and I associate them with the small ponds. Okay, and that can go on for a while. Okay, another type. You notice that there are an awful lot of these types of ripples that are so associated with tidal environments. Another set of terms that pertain to ripples: Flaser, wavy, and lenticular bedding. We use these terms when the deposit is, another word is heterolithic. Heterolithic means that it's composed of more than one grain size. In most cases, we're looking at mud and sand. We could be looking at different fractions such as clay and silt. And we refer to it as Flaser bedding if the deposit is composed, if the ripples are made primarily of sand, and there are thin lenses of mud that are present between those layers of sand, and they can often be quite discontinuous. On the other end of the spectrum, if you look at this picture on the right, just above the pencil, there's an interval down here that is a little bit more muddy than it is sandy. That interval right there, I would refer to as lenticular bedding. Above that, where the mud and the sand are in roughly equal proportions, we call it wavy bedding. And so the only difference between those three terms is the relative abundance of the fine-grained sediment and the coarser grained sediment. Now, back to the earlier idea of why would we get this? What are the processes that are responsible for forming these, rather than just memorizing a pattern? Oh, I see Flaser bedding, therefore it must be a tidal flat, right? Well, what's responsible for it is you have to, again, have two different dominant states of energy. So there needs to be one state of energy that is high enough to carry the coarse sediment, and then a second state of energy that is low enough to deposit the fine. So think back to the Hjulstrom diagram. The energy has to be high enough to transport the coarse sediment, and then it has to slow down so that that very fine sediment can settle out. So again, where is an environment where this is likely to occur? Most commonly, I see this in a tidal environment. And so as the tides come in, they transport the sand, form the ripples. And during high tide, is when water is quiet and relatively still, the mud can settle out and form drapes. And you can actually see the drape pattern over here in the right photo. Forms a drape over the sandy ripples. And then when the tide goes out, it's left behind. The next tide comes in. Another sandy ripple is transported over the mud, and so you can get the interbed of sand and mud. Now, a lot of times, such as this one on the left, where it's very discontinuous, as the tide moves out, it might strip the mud off of the top of the ripples, but leave it in the troughs. That's a very common aspect associated with these. So a lot of times, we'll find the Flaser, wavy, and lenticular bedding in conjunction with the flat top ripples. Okay. Usually I ask if there are any questions, but with so many people in the audience, that's difficult here. Climbing ripples. Climbing ripples occur where there is where there's high energy and there's a high abundance of sand. And the idea here is that one ripple or dune, as you see in this middle picture on the left, is going to migrate over the top of another. And this is what is going to allow these features to be preserved. It looks like the lighting wasn't the best on this picture here, but if you can see these inclined surfaces and the cross bedding that's in between. So here's a ripple, there's the next ripple, here's another ripple, and they stack on top of one another. And so these are going to form where there's a high sediment supply, as I've mentioned, high energy. A lot of times we'll find these in levees adjacent to a river. This particular example is from a bayhead delta in Cretaceous deposits in Utah. At a much bigger scale, where we have the very large sand dune deposits. If you're familiar with the Navajo sandstone in the Western United States, here's a dune, here's another dune that migrated over the top of that dune, and there's a third dune on top of that one. And so the Sahara Desert would be an example where that type of thing would be happening today. So again, I'll show a couple of videos down here. So in this case, it's showing planar cross-bedding, but it's just showing very rapid accumulation. And this horizontal bed that's in between, that's separating, is formed in response to the flow separation that we looked at earlier. Here's an example from a flume. Okay, I'm going to go a little bit further in this one. So there's the previous ripple. The sand's moving up and over the top to form the next. In this case, they've put some coal fragments in there so that we can see the bedding. That's what the dark material is. And they'll back up here in a minute. You'll be able to see the ripples stacked on top of one another. Okay. All right. So back to the flow regime structure. Okay. What we've been talking about so far are ripples, the various types of ripples, and earlier we showed that as flow velocity increases, there will be a transition from ripples into sand waves, into dunes or mega ripples, and then we're going to hit a boundary. As the velocity increases even further, the ripples then start to become smaller. They become broader, but much flatter. And eventually they will flatten to the point that they are parallel laminations. And by this point, there is an almost balance between the rate of erosion and the rate of deposition. Deposition is still slightly higher. That's why they're able to stack on top of one another. The most common place to find horizontal laminations is along beaches. This is a beach in Southern California. It's been cut through by a channel, so you can see the laminations. On the right is an ancient example. This is from the Cretaceous in the state of Utah. I put this one here down at the bottom. There's a channel that had cut through the beach. It's a very similar setting to the one on the left. And here are the parallel laminations that are on the top formed by the beach. So these are produced in the breaker zone. Waves come into the shore. They carry sediment along the shoreline, mostly as sand waves, and then they break onto the coast where they rush up, and this very high energy environment is where we're going to produce the parallel laminations. We can also see these in rivers, particularly in braided streams where there's a high energy condition during flooding conditions, a flooding situation. And so here is a flume example. You notice that the sediment is moving by traction. But if you watch very carefully, you'll notice that the sediment is piling up very slowly. So the sediment is moving primarily in traction, and there's scouring and deposition that's taking place at the same time. Okay. And just an environment. This is a video that why isn't that one playing big? This is the type of environment in which you might find parallel laminations. Okay, again, because of time, I'm going to cut some of those a little bit short. Okay, the next step here. Okay, I have the flow regime diagram in the lower right. So we've gone through the ripples, the parallel laminations. Now, as flow velocity increases even further, we're getting very close to the boundary where we're going to form anti-dunes. Okay, on the left, it's not really common to find these features in gravel. These are anti-dunes. These were formed when a reservoir, there's a reservoir that was placed at the top of a mountain in the state of Missouri. And what they would do is they would pump water up during the day and fill the reservoir and then release the water, pump it up during night, then release it during the day to produce electricity. This reservoir was about, probably half a kilometer long and a quarter kilometer wide, and it failed and had a catastrophic flood that came down through, and so we're able to see these sedimentary structures even in something as coarse as gravel, which is unusual. It's really hard to find examples of anti-dune features in the rock record because they're very short-lived. They're very ephemeral, so they have a very low preservation potential. The example that I'm showing here is actually a volcanic ash here in the state of Idaho. And so as you look at this middle figure, you would probably want to interpret the transport direction as from right to left. Actually, it's from left to right. So notice that the dipping is in an up current direction. And what happens with an anti-dune, in this case, as it's moving from left to right, here's the ripple that's formed. And then it piles sediment on this side and it erodes off the front. And it piles sediment on the back and erodes off the front. And so it's actually piling sediment on the up current side of the ripple and eroding on the down current side. And therefore, as the material moves basinward, the structure itself migrates up current. I realize that might be a little bit hard to visualize, but let me show a few videos. I've got several, even though this is the least likely structure you're going to find in the rock record, I have more videos because it's very interesting. Okay, here's an example of standing waves. This is a creek that is crossing a beach. It is moving very quickly, but you see how the ripples are not moving? So this is again, pretty much a balance between the deposition and erosion, and the ripples are staying put. In the sorry about that, I'm having a problem with my mouse here. So here's another example. Okay, I'm showing these first two videos to indicate that this tends to be a high energy environment. Another one where I apologize. I thought I had these all taken care of last night. Okay, now on this one, notice that the dune is going to form, and then okay, the transport direction is right to left. So sediment and water are moving right to left, but notice that the dune form moves in the opposite direction. So you'll see the sediment is going to pile up, and then it's going to move landward. But then it washes out and disappears. That's one of the reasons that they are very poorly preserved, is that they're very temporary features. Okay, now I'll go ahead and forego the others. And let's see, Saiful, I haven't been paying much attention to time, so if I start to get short on time, let me know.
It's okay, sir. You can actually continue because actually we have actually the shortage after 30 minutes. So I think you can continue, sir. Okay.
All right, now, so what I've gone through up to this point are the flow regime structures. By flow regime, that is, they follow that pattern of getting bigger and then flatter and dunes, and the next step after that is it becomes a channel or some other erosional feature. So this next structure that I'm going to talk about, stratification, a very important sedimentary structure to understand. A lot of people refer to it as hummocky cross stratification. I prefer to leave the word cross out of that. If you look at these two figures left in the middle in particular, notice that the bedding is almost more vertical than it is lateral. There is a lateral component associated with it. Now, these are very high energy units. If I were to place these on the flow regime diagram, it would probably be just after plain bed. And hummocky stratification is thought mostly in response to storms. Storm surges make their way onto land. For instance, in a delta, they'll pick up a large amount of sediment and they'll flush that sediment back out to the sea. The sand is in suspension. This is why it doesn't fit on the flow regime scheme. Is the flow regime scheme refers to a progression through structures that are formed strictly by traction. In this case, we do have traction, but we also have suspension of the sand from the storm. And so as the sand is deposited, there is both an oscillatory flow that's associated with it, and it's going to drop out of suspension. And the result is it forms these features. You can see on the left, these mounds and troughs. The mounds are called hummocks. The troughs are called swales. And you'll see this referred to as hummocky stratification, or in this case, if you see the preservation mostly of the part that has the trough character, we'll call it swale stratification. They're both the same thing. Just depends on how much of the upper part of the structure was eroded and how to which term we will use. I tend to use hummocky for both. But these are a very important sedimentary structure in identifying the types of beach deposits, and we'll talk about this one quite a bit more tomorrow. Okay, but the hummocky has to do with its geometry. Okay, some other sedimentary structures that are significant and don't fit into the flow regime structure that I'm talking about are things such as imbrication. Okay, imbrication, if you look in the right photo, notice that most of the pebbles are dipping to the left. Imbrication refers to the alignment of particles that have an either long dimension or they're kind of flat. So this will be primarily in gravel. As the fluid flows into these particles, if they're dipping up current, it will flip them into the opposite direction, and that's what the diagram shows on the left. And so again, will be relatively high energy, and one of the useful characteristics of imbrication is we can use it as a paleo flow indicator to indicate the direction that the water was moving. So if you look at the picture on the left, the water was flowing from left to right. It seems that in the pictures, not a lot of these are flowing from left to right. So that's are other features that I could talk about that are related to those primarily focus on here. If you want to ask some questions afterward, that'd be fine. Okay, so really briefly, I'm going to talk about some of the flow deposits. I'm cutting those short mostly because of time. But these are deposits that are formed through mass wasting. That is gravity pulling sediment down the hill. So these are not deposits that are formed because water is picking up particles in one place and depositing them in another, but rather this is large amounts of sediment that are breaking loose on a slope and moving down the slope as a mass. When we talk about mass wasting, there are a lot of different ways that this can happen. We refer to rock falls and slides and slumps and so forth. Most of those are occurring up in mountainous areas, and those deposits will not be preserved long-term in the rock record. The deposits that we do tend to have preserved that are associated with flows are debris flows and turbidites. And we find those in a couple of, well, on this diagram here, this is showing a lot of the different types of events that can happen, the different types of flows. This actually can become quite complex. It depends on the kind of material that is moving, the amount of fluid that's present within that material, how steep the slope might be. Climate can have an impact, and they will be different depending on whether they're formed in a subaerial or a subaqueous environment. Okay, and so one of the common features that we see associated with flows is graded bedding, and that simply means that the grains are larger on the bottom and they're smaller at the top. This tends to refer to material that is moving as a fluid, and as the fluid slows down, it's kind of like shaking the bottle. We've all done that, where you shake a bottle, it's full of sediment, and the gravel falls out first, and then the sand, and then the silt, and finally the clay. The same type of a thing will happen here. One place where we might see that the graded bedding is in an alluvial fan, such as on the right. There are a large number of types of flows that can move out onto the fan. I'll show that here in the video in just a moment. The other type of a flow that will form graded bedding is a turbidite, and that will form what we sometimes refer to Boma succession. A Boma succession. This we've got a diagram here on the left, and down at the bottom, a Boma succession, if it's complete, will have an erosional base. And then the first deposit, you can see that flow regime characteristic through here. That first deposit is going to be a structuralist sand. That structuralist sand represents deposition very rapidly under high energy conditions. As the flow slows down, that changes to parallel laminations, which are upper flow regime. And then as the flow slows down even further, it will transition from the parallel laminations. In this case, because of the grain size and the sediment abundance, we don't get dunes, but we do get ripples. And these are climbing ripples in this case. And then when the flow is done, quiet water conditions return, and mud is deposited on the top until the next flow. And let's see, where's my cursor? And you can see the next flow is coming in up here above. So this is a relatively complete turbidite that was formed off of the front of a delta during the Cretaceous. On the right, I have a picture of the fan that is off the mouth of the Mississippi River in the Gulf of Mexico, which would have been a similar environment. And you're looking at it dominated primarily by turbidites. So let's go ahead and look at a couple of videos. So this first one on the land, the thing I like about this video, even though it's very old, is it shows a wide range of types of flows. This one here would be a grain flow. There's very little fluid that's associated with it. And as we go through this video, each one of these debris flows has a greater amount of water associated with it. So in this case, you're looking at a deposit that has very little fluid. Okay, now can you picture what the deposit's going to look like once this exits the canyon mouth and spreads out onto probably an alluvial fan? It's going to have a type of chaotic bedding that's associated with it. Now, even though there is some mixing that takes place, notice on this one and some others, look at that big boulder. The big boulder is really not rotating very much. And often something that you see with debris flows is that the very large particles move to the top. So you have a reverse type of a grading associated with these, whereas finer at the bottom is coarser at the top, and those large particles can actually float on the top of the debris flow. So try to think about what type of a sedimentary structure this is going to produce once the flow is done. Are we likely to see any of those structures that we've talked about in terms of flow regime? Will we see ripples? Will we see dunes? Probably not. Planar beds either. Probably none of those features will be present. In most cases, you're likely to see a thick, structureless deposit that might have some grading, and that's about it. And a very chaotic mixture of particles. Okay, the deposit here is becoming much more fluid. Okay, how big some boulders are. The particles in a debris flow can be huge. Again, notice how some of the very large particles are floating on the top, which is kind of counterintuitive. Okay, they're becoming more fluid now. Okay, there's it's rotating. And often you'll see multiple waves in these. So at the end of this video, we'll see Seifel in his dream job, the reason he's going to school. Okay, this one's quite fluid. Notice the force of these. And these are deposited on alluvial fans. And as I drive through the western United States, I'm always surprised at the number of homes and communities that are built on alluvial fans. With the increased water content, they're moving much more rapid. Okay, so at what point do they transition from debris flow into flash flood? Okay, so we've gone from all rock and very little water to almost all water and a lot less rock. Here you go, Seifel, this is why you're going to school.
Hello.
All right. Now, I don't know why he was catching the dirt. You can always get that afterward. Okay, so graded bedding is something that you'll find in flows and reverse grading. The other thing that is common is the chaotic bedding. So take those debris flows that we just watched and look at this deposit. These are in photographs. On the left is a lahar. That's a debris flow that's associated with a volcanic deposit. This one is from the Death Valley area in California. But notice how mixed it is. Can you see clear bedding in there? Can you see ripples and dunes and planar stratification and all the other things? Basically, it's a large accumulation of very poorly sorted sediment. The boulders can be huge. The one on the left is subaerial, with a volcanic eruption back in the tertiary. And on the left, this one's got small particles. This one, okay, this is a road, so you can see the size of a small car. That big boulder right there. These are from the Permian in Texas. These are debris flows that formed subaqueously. It doesn't take much of a slope, just a very few degrees, and these very large particles can be transported long distances. Okay, and so those are the subaqueous debris flows. Now I'm going to go back here for a moment. I talked about the Boma succession a little while ago, and that one is formed through turbidites. So here is and have I done it again? I've done that again. So excuse me once more while I fix this. Oh, that one says it's right. Okay, I don't know. Oh, yeah. Oh, we'll try it again. Okay, I don't know why that one's. We'll do it this way. Okay, a turbidite. A turbidite is a gravity flow that occurs subaqueously, and it's much more fluid in most cases than the debris flows. In this case, you can see the turbidite moving through all the various components. The head tends to move faster than the part behind it, and this one actually should have sound associated with it. Okay, those are from the side, and here it is from the front. These things can be quite formal. In the early 1900s, there was a turbine off of the coast of Canada that moved across the Atlantic Ocean and was strong enough that it snapped all of the telephone cables that connected the two continents. Okay, this one is showing when it enters a basin, it was confined before, notice that it spreads out. And they put the rock there to show what happens if the encounter obstacle. These tend to be clouds, and we'll go ahead and cease it there. They tend to be clouds of sediment, and as they slow down, they form a deposit like the one that you see in the middle. As we go from very high energy to lower energy deposits. All right. Get back into this. Okay, and I think this is the last structure I have on here. Okay, I just want to real quickly address structureless deposits. Now, in this one, I've chosen a conglomerate. It probably is pretty much structureless within. Now, a deposit that truly does not have sedimentary structures within was probably formed in one of two ways. Either it's a massive deposit, such as the debris flow that we saw, that then slows down and stops abruptly, so that there is not time for sedimentary structures to form, so that sorting doesn't have time to take place. Or the opposite extreme might be in a marine setting, where there is a continuous rain of sediment, where the rate of sedimentation doesn't change, and so there's really nothing to create the bedding. For bedding to form, regardless of the scale, from laminations on sand dunes through these large debris flow deposits, there has to be something that changes between each one of those beds. A change in grain size, a change in composition, a change in some character of the sediment allows the bead to be visible. In most cases, at least in my experience, when I'm dealing with sandstone, and I see a deposit that looks structureless, it's because the sand is very well sorted. The grains are all the same size. The structures are in there. There's probably trough cross-bedding or planar cross-bedding or one of the other structures in there. You just can't see them because of the uniform size of the sediment. So we have to be a little bit careful on using structureless as a feature to interpret a body of sediment. We need to look at what's above it, what's below it. So it's very possible that there's structures that are within, but they're simply hidden. Okay, and that's what I have for today. And so with that, I'll turn it back over to Seifel and let you decide how you want to handle it from here. I hope that I gave to you what you wanted.
Okay, we had some questions in the chat while the lecture was going on. So
Okay,
I'm going to
can...
read them out one by one, and you can answer them. The first one was from Junaid Khan Shezan. Maybe he asked about the imbrication, that how the elongated particles align with the upstream direction.
On the imbrication?
Yes.
Okay, let me let's see, do I dare try to draw something here? I can't find my drawing board. All right, okay, and I can't see me on there either. Can you guys see me? Can you see my hand?
Sir, we are not seeing you.
Because I have my video on, but it's not showing me right there. And let's see, and I don't see access to a drawing board. Okay, I'll just go ahead and try to explain. If you know, maybe take your hand or take a book or a piece of paper and hold it inclined. Let's say that have it dipping to your your right. If you were to push on that from the left, let me see. I'm gonna try it a different way. So you can't see me at all?
No, sir.
No, sir.
Okay. All right. So if a particle is inclined, and let's say that it is dipping to the right, if a force comes from the right against that, can you see how that force is going to hit that flat particle? It's going to hit a book or your hand, and it's going to move up and over the top. But what happens if it comes from the other side, where there's kind of a lip that's extended into the extended above the surface? It's going to catch that particle and it's going to flip it over so that the flow can move across the top of it. I wish I had a way to draw here. That's odd that normally there's a drawing board on there. I don't know who asked the question. Whoever asked the question, did that make sense? And that was kind of an awkward, clumsy way to explain it.
Shezan, you can just turn on your mic and say what your question was, explain what your question was, and did you get...
Okay. Okay, I couldn't hear that very well. Would you repeat, please? I didn't hear that question.
Ethan, can you please turn on your mic and you repeat the question once again to sir about which part of the question you were truly confused of? Thank you.
Can you hear me?
Yes, I can.
Oh, my question was that how elongated particles align with the upstream direction in strong currents. I just couldn't visualize the 3D situation.
Yes,
Please, can you explain?
Okay, that's why I'm trying to get my video to work so I can show you. According to this, you should be able to see me. Okay. Do you have a book or something in front of you?
Yes, I do have one.
Okay, so take the book and put one side on the table and hold the other side up with your hand so that it's inclined.
Yes, I've done that.
Okay. All right. So if you take your hand and you push from the let's say the down inclination side, and you push against that, what does your hand do? Do you see how your hand just moves up and over the book?
Yes, my hand is
Okay.
going
Now,
ahead.
what happens if you push your hand from the other side? It flips the book over.
Yes, it actually bends, but
so if on the up dip side of the particle, the particle is likely to be raised partway above the bedding plane, and so that's going to allow the water to hit that particle, and the force that's exerted is going to flip it over so that it's in the direction of least resistance. Did that help at all?
yes, I could visualize it a little bit.
Okay. Let's see. For a drawing board, does somebody from your side have to give me access to that? Now, when I host a meeting, I usually have a drawing board on here. But, okay, but did that answer your question? Any others?
Sir, there's another question from Muhammad Sulaiman. He's asking, quote, are there any parameters of dunes on which the flow separation depends?
Yes. Let's see. A lot of times in thick dune sequences, let me see if I can bring up a picture. I'm going to bring up a picture from another presentation, and I'll show an example of that. It opens here. There we go. All right. Go back to share my screen. And okay, can you see my screen?
Yes, sir.
Yes, sir.
Where?
Yes, sir.
So
We're seeing your screen.
all right, so okay, here's a modern dune. Up the upwind side, sediment's been carried by traction. Then you see the flow separation at the crest, as I showed before. Here's an example of the Navajo sandstone in Zion National Park in the state of Utah. And on this, you can see the steeply inclined beds that are the ripple form, the dune form, as it migrates through traction. But in between those dunes, do you see these these more flat intervals? In some cases, those are the finer sediment that has landed on the dune before. So there's erosion at the top of the dune that's in front. This is the sediment from the flow separation that falls on top of the dune, and then the next dune migrates over the top of that. Does that answer it?
Yes, sir, that's answers it.
Okay.
The next question was from Anika Nawar. She asked, sir, would you please describe the modified Hjulstrom diagram once again?
Sure. Let me go back to the diagram. Okay, so on this diagram, the yellow in the lower right is the condition under which sediment is deposited. The blue at the top is erosion. So notice that off on the left, here's flow velocity. So down at the bottom, you have a flow of 0.1 centimeters per second. Up at the top, 1,000 centimeters per second. The horizontal axis We're moving from clay to silt to sand to large boulders on the right. And so what this shows, let's start with the top. There's a line down at the bottom of the blue. That line is the velocity at which that particular grain size will start to move. Now remember, this is unconsolidated sediment. This is not eroding rock. This is unconsolidated sediment. And so clay, the finest clay, does not start to move until we have flow velocities that are well above 100 centimeters per second. Sand starts to erode when we have flow velocities that are a little bit above 10 centimeters per second. Gravel, again, has to be very large. Now the difference is that in this case, going to the right, it's easier to move small particles than it is to move large particles. But as we go to the left, it becomes harder to move the small particles because of the kinds of particles. When we get into the clay fraction, we're looking at particles that have electrostatic attractions and other things that cause them to stick to one another. So you have to overcome some forces other than just the particle size to cause the sediment to begin to move. Now on the other end, once those particles have been trained, have been eroded, are moving, then they will stay moving through the velocities in the gray area. And over here, when the flow velocity, so the gravel needs the flow velocity needs to be here for erosion to occur, but then when it slows down just a the flow velocity is here for finer sand or somewhere in between. Did that help?
Yes, sir. Thank you so much.
You're welcome.
Okay, and if anyone else have any other questions, you can unmute your mic and ask the question to us, sir, directly. Thank you.
Sir, I would like to ask you a question about the slides where you showed the difference between planar and transverse beds.
Sure.
Sir, the question was, normally during fieldwork, when we observe a section, we don't mainly observe it in a 3D view, like the ones you showed in the videos,
Right.
The moving videos. So in those cases, mostly we misinterpret parallel laminations with planar transverse beds because we are only seeing one side of the longitudinal section. So is there any technique or process how we can identify them properly in the field?
Yeah, okay, something like this one right here, looking at this particular outcrop, I can only see one direction. Okay, so it looks like the dune is moving from right to left. Is it really moving from right to left, or is it coming somewhat in the screen and out of the screen? And so the three-dimensional diagram off on the left, shows how that varies depending on your perspective. So what I would have to do right here is I would need to look for more than one exposure. And so here I can see one face, but maybe I can see another aspect here at the top. Or if I come around the corner, maybe I can see another aspect of the dune. So the main thing that you're going to have to do is you can't take the measurement only right here. You're going to have to find an exposure where you can see more than one aspect of that structure.
Thank you, sir.
Okay. Did that answer the question?
Yeah.
No, but no, that's a very good point, because we all do that. When I look at this, I think, oh, the flow was from right to left, but it actually might have been, into or out of the at some angle. And so you're absolutely correct. From one face, you really can't tell the true direction of dip. Now, another thing, if you have just a vertical face and you really cannot find other views, the steepest angle is the one that will be closest to the true photograph. Okay, and same thing on this one here. we actually do that exercise on this outcrop right here. You can see it looks like the flow is from right to left, but up here on the top where the surface has been exhumed, we can actually put a compass and measure the flow direction from that point. Okay, other questions?
Have anyone any other questions? Okay,
I'd like
I think.
to ask a question.
Okay, go on.
Okay, sir. So in graded bedding, we know that the coarser grains are on the bottom and they become finer upwards. But in case of an overturned strata, the coarser grains would be on the top. And in a reverse graded bedding, the same thing is seen. So how can we distinguish between an overturned graded bedding and a reverse graded bedding?
Well, in that case, you might have to look for some other features. Are there some erosional structures on the base, such as flute casts or load casts or tool marks? Also, you might need to look at what deposits are above it and below it. Do you know the stratigraphic order? In most cases, if I'm dealing with a stratigraphic succession, I know that it's overturned because on a much larger scale, or overturned or not overturned, because on a much larger scale, I know what the formations are, and I know what order that they should be in, and the entire thing is overturned. So it's not just one unit will be overturned. So you might have to look at the entire stratigraphic package. You may not be able to tell entirely from just that one deposit. But the other thing is, what kind of a deposit is it? In a debris flow, you're more likely to see reverse grading, and in a turbidite, normal. In a cut and fill structure, the channel form at the bottom, and then we'll have the normal grading that's present within. So your interpretation of depositional and might be a key as well.
Okay, thank you, sir.
You're welcome.
Any other questions from the audience? I guess there is no other question. Okay, thank you very much, sir, for this mesmerizing presentation. We are very sorry for the technical inconvenience. Actually, I've been through a tensional situation in here. Actually, we have tested the techniques a couple of days ago, sir, and everything was okay then.
Yep, that's.
My heartiest gratitude goes to again William, sir, and dear audience, Lubna from Morocco. Pardon me for this feeling. I am sure almost every participant have acquired some valuable knowledge from this. To meet my concern, a quiz session will be held at the end of tomorrow's session. The participants of the quizzes will be received a verified certification from UDGS for attending the consecutive session. And tomorrow has an advanced application to field studies of the sedimentary structure will be discussed. And so we'll see again in tomorrow.
Good.
Sir,
Now,
okay, sir. Thank you very much, sir.
Okay. Now, tomorrow we will have an actual field application associated with this. I hope that this wasn't too elementary for the audience, but we'll take it up.
Sir, I think it is actually a very big discussion, actually, and it is very understandable for all type of audience.
Well, thank you very much, and we'll talk to you tomorrow. Feel free to contact anybody by email. I'm happy to answer more. You're welcome. Okay.